her talk is circles and circular counting, and she's also the writer of PhD plus Epsilon. It's a cool book.
Oh, thanks.
Yes.
Well, first of all, thanks for reading my blog. And thanks for inviting me to speak. Yeah, so this is a talk about arithmetic geometry, but arithmetic geometry, and this is going to happen a lot during this talk. There's things that are not very clearly defined anywhere, but you kind of know it when you see it. Do you know that kind of definition? And so this is why I decided I would do lots of examples today. Sort of get to the idea of what arithmetic geometry is and what kinds of things I do in my research. And so the first thing I want to start with is just a very simple example, and it's sort of in the title. So let's start with this equation. Okay, very, very simple. It's an equation, a polynomial equation in two variables, x squared plus y squared equals 1. There are lots of questions you could ask about this equation, but questions that number theorists are interested in are questions about numbers, right? And so, for example, what numbers satisfy this equation? And so I could ask, what are the solutions? Let's call it Q1, because I'm going to ask lots of questions. In R2. Okay, and R2 just means pairs of real numbers, right? And so I want to see, or I want to know, what are the real numbers that satisfy this equation? That's a question about numbers, and then this is number theory. Very broadly defined, right? But it's a very specific question about numbers. And so instead of answering this question in general, maybe we want some examples. So any ideas of what are solutions to this in real numbers? There's some easy ones. 1, 0. Yes. Another one. 0, 1. Okay. Now something with no zeros. So this is true too, right? Now something without zeros. Sorry? 1 over square root of 2? Right? That's one. Another one?
All the sines and cosines of the same theta values?
All right, well, sort of like 3/5, 4/5 is another one, just to have one there, right? So we have a nice set of examples. That doesn't answer all the questions. What are the solutions in R2? It doesn't give us all the answers, right? And I saw someone going like this, because this question is much easier to answer with a picture, right? What's the picture? What does the set of solutions look like? It's the unit circle, right? And so that's almost a circle and almost centered at 0, but believe me, it is. And this is sort of my my example for everything in arithmetic geometry or arithmetic, yes, arithmetic geometry, not algebraic geometry, arithmetic geometry, is that there's a question about numbers that makes a lot more sense when you talk about the geometry of the question, right? Does everybody agree with this? Okay, so this is nice. So sometimes it makes more sense. So this is what I'm going to call question 1.2 is, what does the set of solutions look like? Okay? Sometimes this question makes more sense than that question. Okay? So let's change the question a little bit. So this is question 2. What are the solutions in Q2? Now we're starting very simple, and it's going to be less simple by the end. But so I'm just changing the set of numbers that I want as answers, right? So I was looking for real numbers first. Now I only want rational numbers. Okay? And so in this list, you can see some of these work and some don't. There's one that doesn't. Which one? This one is not an answer, right? This is not a point in Q2, but all the other ones are, right? And in fact, let's just look at this one. The other ones are really silly, right? But this one is nice. So 3/5 squared plus 4/5 squared. We all agree that this equals 1, right? And in fact, this is equivalent to this, right? And this should make you think of a 3, 4, 5 triangle, right? And in fact, we say that 3, 4, and 5 is a Pythagorean triple, because it satisfies a relation like this, right? And so now we have a different way of thinking of this problem. We have, okay, so we want rational numbers to satisfy this equation, and that is equivalent, by what we just drew, to finding rational points on the unit circle, right? So we are also trying to find rational points on unit circle. But now we know it's also equivalent to finding Pythagorean triples, right? For every rational point here, I can find a Pythagorean triple and vice versa, right? So now we have 3 equivalent problems, and they're all equally difficult. And so I'm just going to answer this question, and then you'll believe me that I answered the other 2, right? And so the trick here is we construct, so let t be a rational number. So it's a number in Q. Okay? I'm going to draw a line. So this is the point -1, 0. I'm going to draw a line that goes through this point, so LT, that has slope t. Line going through -1, 0 with slope t. Okay? And so this has to intersect the circle at another point. Do you guys agree with that? And let's say these are the coordinates of that point. Okay? So this line, LT, intersects the circle at the point PT, QT. And so my claim is that this point has rational coordinates. There are many ways of seeing this. Any ideas why this is true? Well, if you have no idea how to start, how would you answer a question about what is the intersection of 2 equations? Right, you just, you know, I mean, do we know exactly what the equation for the line is? Well, we have a point and the slope, so we can use the point-slope formula, and we know exactly what the equation is, right? And all we have to do is figure out what is a solution of both this line and this circle, right? So we just do some algebra, and you can find exactly what coordinates these are. So you know, proof, exercise. Gil is going to quiz you on this next week, so you better know this. But it's not a terribly complicated exercise, right? It's just some computation that you guys can do. And then what's nice is that it's clear that these are only functions of t. Right, both of the coordinates are functions that depend only on t, which is a rational number, and you get rational expressions, and so you know that they have to be rational points. Okay? And so this is a homework problem for you guys. And so, but this is nice. So if I have a rational number, there is some function that gives me a rational point on the unit circle. And in fact, here's my next claim. The map from Q to rational points on the unit circle, except -1, 0, which we know is a rational point, but we're not going to get this way, right? Do you guys agree with that? Okay. And so the map that goes from Q to rational points by taking T and mapping onto PT, QT, as I just drew over there, is a bijection. And so proof, homework number 2. What do you have to prove to know that it's a bijection? Injective and surjective, exactly. So you need to show that it's injective and surjective. Injective is kind of easy to see from the picture, right? You're not going to get from 2 different rational numbers the same line. And surjective is a little bit tricky. You have to make sure that you know what rational point you should plug in there to get, what rational number you should plug in to get a particular rational point, right? And so, but again, this is a fun exercise, and it'll be on the exam next week. So, any questions about this? So this is neat. I really like this problem because it shows us a little bit that to answer this question, we kind of have to think about the geometry, right? This idea of drawing a line and seeing where it intersects the circle gives us all the rational points, or a way of getting all the rational points, right? And so what we get for free is now we have a system for finding Pythagorean triples, right? So that's also nice. And so, we can answer, this is a really classical number theory problem, Pythagorean, right? But we can answer it using geometry. Okay? So I think that's really neat. Let's ask a stupid question now. So question, that was 2, so this is question 3. I can keep changing the set. So why not, I did real numbers, I did rational numbers, why not integers? Why did I say it was stupid? It's easy, right? We already have the answer. It's these 4 numbers. This. Right? So, done. That was easy. So, let's just write it down. Plus or minus 1, 0, and 0 plus or minus 1. And there are no other solutions in the integers, right? And so let's ask something more interesting. Let's say I'm taking the integers, but I'm modding out by 3. So does everybody know what this means? So mod 3, so we're just looking at integers, pairs of integers in z mod 3z, so integers mod 3, right? If you don't know what this means, does anybody not know what this means? Okay, because I can take 2 minutes to explain what that means or to remind you guys. So this means that we're only looking at the remainders of when we take an integer and we divide by 3. So there are only 3 things that we could possibly get, right? What are they? 0, 1, and 2, right? So the set z mod 3z is 0, 1, and 2. And then the way we add numbers is we always look at the remainder after we add, right? Or multiply or anything. And then this just means pairs of those. So how many possible solutions could we have? 3 squared, right? That's the most that we could have. Before here we had infinitely many, there we had infinitely many, here we had finitely many even though it was an infinite set. But here we know that there's finitely many solutions, right? And what are they? These are also kind of easy. They're going to be 1, 0, 0, 1, and then 2, 0, and 0, 2. And that's everything. But, if you having finitely many options makes it easy to just try each one, right? And then eliminate the ones that don't work, right? So this is what's nice about finite fields or finite sets, is that you can do things like that. So you can have, if this is much bigger and you don't want to do it by hand, you can ask a computer to do it. Because there's only finitely many things to check. And computers do things like that pretty fast. Some of those things. And so let's check one of these. So for example, 2 squared plus 0 squared is 4, which is 1 mod 3, right? I'm just doing this so that we get used to the mod language. I know a lot of you nodded when I asked if you knew this, so bear with me. And because this was, to begin with, a finite set, so we could only have finitely many solutions, then so like before we had the geometric question that came with with the unit circle. And now we have another number theoretic question, or a counting question, which is sometimes it makes sense to say, or a lot of times it makes sense to ask, how many solutions are there? And of course, when it's infinitely many, it could be infinitely many like rational numbers, or infinitely many like real numbers, which are different infinities, right? And so this can get, I mean, saying infinity only gives you some idea of how many, but it's more interesting when there's finite things, or well, maybe there are no solutions, and it's also interesting to study why there are no solutions, right? But, so these are sort of questions, and so, okay, because I wrote the question, I should write the answer, so there are 4, right? And so these are sort of all the questions that I could think of asking about the unit circle. And so, before you all get bored with my talk about only circles, let's just change this example a little bit. Instead of x squared plus y squared, so I was changing the set, now I'm going to change the equation. Okay, so I'm just going to do this, where now n is greater than 2, because we covered the n equals 2 case, right? I know some of you know what I'm getting at, so don't spoil it. So I want to understand this, and I'm just going to ask one question. I mean, I think out of all these questions, the most interesting one was the rational points one, right? And so let's just ask the same question. So what are the solutions in Q2? Again, we have the same easy solutions, right? What are the easy solutions? Right. But which ones are solutions always? 0, 1, and 1, 0, right? And then if n is even, we get 2 more. We get negative 1, 0, and 0, negative 1, right? So those are simple. And the question is, are there any others? So suppose there are, then what does this mean? Suppose that we have a solution. Let's say that a over c, b over c is a solution. Why did I pick the same denominator? Because you can, right? Like even if they didn't have the same denominator, I could find a common denominator, right? So this is, let's assume this is a solution, right? And so that means that this equals 1, and like we did with the Pythagorean triples, this is equivalent to saying that this has a solution. Now there's a problem with this. There is a theorem that says no 3 integers, positive means non-zero, a, b, and c, satisfy a to the n plus b to the n equals c to the n for n greater than 2. Okay? And this is known as? Yes, this is Fermat's last theorem. So we have no hope of finding solutions for this. So other than these trivial ones, which we know are, these two we know are solutions, right? And these two may be solutions, but that's it. And so there's not enough room in this board. I'm kidding. But but I'm definitely not going to prove this theorem for obvious reasons. There's not enough time in the semester for me to prove this. But the proof is about 100 pages long. I just want to let you know. And uses a ton of previous results. So if you really wanted to understand this, you would need at least a semester to really get through the previous stuff too. And it was stated, I always forget the dates, this conjectured by Fermat in 1637, and then eventually proved by Andrew Wiles, but after a lot of previous work that helped him out in 1995. So it took a little while, a lot of work. It uses a lot of really difficult mathematics. But this is one thing that I love about this problem, is that it's so easy to state. Can you find, no, you cannot find solutions to this equation where they're all non-zero and n is greater than 2, right? You can state this to your, I don't know, 8-year-old niece, like I have one, and I can tell her this, right? Maybe. I don't know. She doesn't like math, so maybe not. But it's a very simple statement, a very, very tricky and involved solution to the problem. And so, I don't know, I like that. To me, that's fascinating. To other people, that may be daunting. I don't know. It is daunting and fascinating. Actually, I'm not saying I don't get frustrated with this kind of thing, but I like it. So now I think I can give you a sort of wishy-washy statement about what arithmetic geometry is. So it's the study of the solutions in k to the n of a system of polynomial equations in n variables with coefficients in k, and this, where k can be things that we talked about, like, well, let's just say in a ring k, that might mean something to some of you. K equals z, or k equals q, or k equals z mod pz, where p is a prime. Okay? So, well, that wouldn't have to be a prime, but we usually like primes. And so that's it. That's the definition. That's a definition of arithmetic geometry. So this is what we've been doing. We've been looking not at a system, just one polynomial equations in 2 variables with coefficients. Well, the coefficients were always in z, but we were trying to find solutions over different rings, right? And so this is, yeah?
So far, it just looks like algebraic geometry, though.
Oh, well, so the arithmetic geometry part is, I mean, it is in the intersection of number theory and algebraic geometry. And so, I mean, they are very similar, except that in arithmetic geometry, you're more interested in the number theory applications and the number theoretic questions. So, for example, Fermat's last theorem falls into the category of arithmetic geometry more than algebraic geometry. And algebraic geometry is actually a tool in proving. So, and this is one of the tricky things about number theory and arithmetic geometry, is that you sort of borrow from every area of math that you can to solve your problems, which is another thing that I really like. But you're right. I mean, they're very, very closely related. Any other questions? So, I mean, I haven't told you too much. Like I said, this definition is not really a definition. In keeping with the algebraic geometry, some of you may have heard the word variety, and this is what we call the set of solutions to certain systems of polynomials, okay? And so, so sometimes that might slip. I'm going to try to just say equation, solution of an equation, but I might say variety. And also, when I say solutions, I may say points, and now you see why I think of solutions as points, right? So, okay. So now, for example, another famous sort of topic in arithmetic geometry, and a very rich topic, is the theory of elliptic curves. Okay, and so there's many sort of applications of elliptic curves and many reasons why people study them, but this is one example of something in arithmetic geometry. So the questions, like I said, that we like to ask in arithmetic geometry is, given an equation or a system of equations, are there any rational points or integral points or points with, you know, coordinates in a certain special set, right? Those are questions that we like. Are there any? If they're not, why not? And so these are things we call obstructions. What do the solutions look like? I said sometimes Now, you can't always draw a picture like with the circle. If it's more than 3-dimensional, you have no hope, right? But you can still talk about geometry of things that you can't draw. There are geometric properties to these things, to these varieties or sets of solutions. And then the question that I'm especially interested in answering in general is this question of how many solutions to equations, certain equations over finite fields. And this is the part that's more number theory. Like, we like things in finite fields, okay? So this is the question that I look at in my research. And so I thought that for the second part of the talk, my hair is, okay. So for the second part of the talk, I would talk about an equation that I studied in my PhD thesis. So I did my PhD here under Fernando Rodriguez Villegas, who's no longer here or maybe back, I don't know. But this is an example of things that I looked at. So this third example, and so it looks a little bit different, but not too different. So I'm going to look at an equation in 2 variables, but it's cubic. And then there's this extra thing called lambda, which is just some integer. Okay? And in fact, when I have equations like this, where there's some unknown parameter in the integers, we call this a one-parameter family of equations. Okay? So I'm looking at this equation, but I'm looking at lots of equations at the same time, right? I mean, this is unnecessary, but I'll do it. So if lambda is 0, I'm looking at this equation. If lambda is 1, I'm looking, that's the one that's not there, etc. Right? I mean, but I'm looking at all of them simultaneously using that parameter as some unknown integer. Okay? And so I, like I said, like to think about how many solutions. And so instead of just doing Z mod P in general, I just like doing things concretely, especially when, I don't know, I think this may be a little simple for you guys, but it's okay. It's not bad for you to see easy talks every once in a while. So the question I want to ask, a very specific question, is what is the number of points, remember that's solutions, over Z mod 7Z for each lambda, right? Because now I have this lambda parameter, and so I need to know this number of solutions. The nice thing, well, it's not necessarily nice yet, but it might be clear that this is going to have some number of points on it, right, over Z mod 7Z. And this is going to have a number of points on it. It might be the same, but it might be different. But definitely the only thing it depends on is what is the value of this lambda, right? And so, in fact, I'm going to call the number of points n of lambda because it's a function of the parameter, correct? So now that I've written it as n of lambda, the question becomes, so remember that I'm just trying to change the question to something that I can answer more easily, right, or more interestingly. So in this situation, instead of asking this, is what kind of function is this? I mean, this may be completely random, right? But it may have some nice formula. And so if it does have a nice formula, what is that formula? Is it a polynomial? Is it a rational function? Not a rational function? So it should have integer values, right? But we know the output is an integer. But we don't know what the formula looks like, right? And so okay. And so what kind of function is this? Is there a pattern or formula, right? And the answer is yes, there is a pattern and formula. This is, in fact, not always, but for this example and similar examples, this is in fact a very special function. So this leads me to wishy-washy definition number 2, which is what is a special function? So as the name suggests, it's not going to have a very formal definition, right? I mean, you call something special, what do you really mean? And so this is even more hand-wavy than my definition for arithmetic geometry, because I mean, I don't even know what a definition of a special, I can't even write it down. But these are functions that tend to show up in applications. So like differential equations. Oh, well, the differential equations for these special functions show up in applications in engineering, in physics, in lots of different situations. So what makes them special is usually that they come with a differential equation or an integral. Okay, so some examples, and again, I'm gonna just define this with examples and hope that you are satisfied. So what is a function? Well, let me ask you, what should be a special function? Of the functions you know, what should be special? Unless you already know what special functions are, and like, maybe you can tell me. But so the zeta function, it's special in lots of ways, but I don't know if it's a special function. So the exponential function, that's a function that appears in lots of applications, right? Anything that has like exponential growth, so physics, engineering, biology, it has a very specific differential equation associated to it, right? Logarithms are also special. They are more associated to an integral, right, rather than a differential equation, but they're the inverse of exponential, so it makes sense that these two would both be special. Sine, cosine, and trig functions in general.
You're talking about slope functions?
So, yeah, so special functions, as far as I understand them, have to have some sort of well, they have to be smooth because they satisfy a differential equation. So they have to be differentiable in some way, right? And so Bessel functions show up in engineering. If you ever took a differential equations class, you may have seen Bessel functions. And then, I mean, the list goes on and on. There's books in the library, like thick books that are called special functions or tables of special functions. You can see lots and lots of these. I'm just saying some. And then the one that I care about, because it shows up, it's that kind of function, are called hypergeometric functions. And these are actually not as well known as the others. Well, obviously not the first few. And so what I want to do now is talk a little bit about hypergeometric functions and sort of what they are. So they were first defined as many interesting things by Gauss. And so he defined them. You have given 3 rational numbers. You can define a hypergeometric function. And these indices I'm going to explain later. So you have alpha, beta, gamma of z. This is actually a function in the complex numbers, but it doesn't matter. It's a series, power series, with these coefficients, which I'm going to explain in a second. K factorial z to the k. And this symbol is what some people call a rising factorial, or you can think of it as a backwards factorial. You start with x, and then you add 1 until you get to k minus 1. Okay? So for example, what is 1k? It's going to be k factorial, right? Because you start at 1 and you end up 1 plus k minus 1. So this is exactly a factorial, right? But the nice thing is you can plug in rational numbers in here and it makes perfect sense. So like, what is 1/2 3? Well, it's just 1/2 times 1/2 plus 1 times 1/2 plus 2, and that's like 15/8, right? So it makes sense to plug in rational numbers. That's the only thing I'm saying. There are some restrictions. This is a power series, so you know it has a radius of convergence, right? So it's not going to converge for any alphas and betas and gammas, and it has to, I think absolute value of z still has to be less than 1. Yes?
What is that function called again?
The Pochhammer symbol. This is why I didn't say it, because I don't even know how to spell it. So I think it's Poch, and then you have 2 H's. I think. So this is the Pochhammer symbol. Okay? And you can also call it, I think this is more traditional, the rising factorial. Or just, if you take a combinatorics class, they might call it this. People who do hypergeometric function stuff call it Pochhammer symbol. I don't even know if I'm saying it right, but this is, so that is Gauss's hypergeometric function. And so you can see that you can sort of maybe imagine how one would generalize this, right? So this is just saying, so you have 2 parameters in the numerator and 1 parameter in the denominator, right? And so you write the numerator parameters up here, and you write the denominator parameters here. And for it to be Gauss's version, it needs to be exactly like this. But you could imagine having like n numerator parameters and m denominator parameters, right? Maybe? I mean, you can generalize this as much as possible, and you can generalize it so that it has less parameters, right? So we can say instead of 2f1, we can see 0f1 or 0f0. And in fact, notice what happens when I don't have any parameters. So if I block this, what do I get? It's the exponential function, right? So in fact, one of these special functions is actually a hypergeometric function. It's just 0f0 of z, right? Where we don't have any parameters in the numerator or denominator, right? And this kind of function satisfies what I will call nice, in quotations, differential equation. But I will leave it at that, because that should be satisfactory. Nice. Nice is just, it doesn't have too many singular points, and it's just, it satisfies some nice properties, whatever. This is my wishy-washy talk. So, and then notice that if all of these were 1s, so that's my other example. So 2f1 of 1, 1, 1, z, what is that? It's just the sum of z to the k, right? And that's called the geometric series, right? And this is where the hypergeometric names come from. Okay? If you have these simple parameters, it's geometric. And if you add sort of weirder parameters, it's hypergeometric. Okay, so I mean, it's really a weird name, given that it seems to be the only reason people called it that. But okay, so I completely got sidetracked explaining what hypergeometric functions are, but you know why? Because I wanted to answer this question: what kind of function is the number of points as a function of the parameter, right? And so this is a special function, and in fact, it is a hypergeometric function. But I will have to modify some things. So remember, this is the equation that we're looking at. So x cubed plus y cubed minus 3 lambda x y squared equals 0. And so for some reason that I'm not going to explain, I'm not interested in n of lambda in general. I'm interested in n of lambda mod 7. Okay? So n of lambda is some integer, right? And I'm going to take that integer and mod it out by 7. This is what's going to give me my pattern. Okay? And so n of lambda mod 7 is some constant that we're not going to worry about, plus 2f1 of 1/3, 2/3, 1/2 evaluated. So remember, this is evaluated at z. I'm going to evaluate this at 2 squared lambda cubed. And then plus 2f1 of 4/3, 2/3, 1/2, 1 over 2 squared lambda cubed mod 7. But there is a tricky part, which is these are infinite series, and this is something mod 7, so it should definitely, like, there's going to be some weirdness. But so I'm going to do this, which I'm going to explain in a bit. This means, so this is an infinite series. This means I'm going to truncate it and only look at the terms from the 0th term to the first term. Right, so if this was a to b or 1 to 15, those are the only terms of the series that I'm going to look at. Okay, so k equals, now it's not going from 0 to infinity, but from whatever I put as my lower bound to my upper bound. Okay, in this case it's silly. This is, the problem is I was trying to adjust an example I did in general, and then after I did everything, I realized 7 might not have been the best prime. But and this, if I don't finish it, means I'm just looking at the third term. Okay, and so it seems way too complicated, right? And it is, because in reality, I mean, if you calculate all that, which you can using those things and then some mod 7 properties. Like, for example, 1/3 mod 7 means the inverse of 3 mod 7, right? So whatever you multiply by 3 to get 1, right? So those are things that one can do. And so this would be that constant that we don't worry about too much, plus 1 plus 4 lambda to the 4th mod 7. So that's the real pattern. So I know you may be asking, why do that when this is the answer? This seems like it would be easier to get some other way, right? And in these smaller cases, yes. In fact, you can just tell a computer, I eliminated the example, but you can pretty much just plug this into a computer. It's just 2 loops of mod 7, right? You only have to look at 7 squared things. So it's not that difficult. But I mean, of course, if you want to have a function of lambda, it might be a little tricky. But you can check that this is the pattern. But the reason to do this is generalizable. And so I definitely gave you, so you can have mod p for any prime p. So that my solution includes any prime, not just 7. And it has, instead of degree 3, like here, I can do it for higher degree. And in fact, you can do it for higher dimensions. So more variables in the polynomial. It's a polynomial, more variables. Now I have to remember what I did. And you can even do like mod or over a finite field of q elements. So this is what we call f cubed. You don't have to know, but it's a set with q elements that satisfies some special structure properties, and it has size a power of a prime. Okay? And so I think this is nice that the reason I tried to get it like this was so that I could generalize that. I also was trying to generalize a theorem by someone else on elliptic curves, and so I was trying to change that to a different set of equations. But I think what's most interesting to me, and this is because I'm a number theorist and I'm mildly obsessed with hypergeometric functions, but mostly the number theory part, is that this highlight that there's I mean, this is not the only situation in which you find hypergeometric functions, right? I mean, I just said that these are all other situations where hypergeometric functions show up, right? And I think, to me, this highlights that these functions are special in a different way. They're functions that appear when you're counting points over certain varieties. Okay, and I think this was sort of a big project that I had for my thesis, and we weren't able to say anything that general. But this is the suspicion of everyone who works with hypergeometric functions, and that they have this very close relationship to arithmetic properties of a variety. So numbers of points, those are arithmetic properties. And they also show up when you look at the geometry of the varieties. So there are certain geometric features that have to do with hypergeometric functions. So it's sort of a magical, to me, a magical function that shows up when you're not expecting it. And these are the kinds of things that the number theorists and arithmetic geometers are interested in answering. So just to let you know that I'm still working on this. So that was my thesis. Now I'm working on a family that looks like this. I just wanted to say this because this is like the last month of my life has been this. So I've been looking at this family, and so far it does seem to follow the same pattern with the hypergeometric functions, but that constant c, which is easy to determine here, is very hard to determine here. So I'm just going to throw, for the last 5 minutes, I'm just going to throw some big words around and just to get the buzzwords out there. So this is what you call a K3 surface, or an example of a K3 surface. These are interesting to people in many different fields. These are examples of what people call Calabi-Yau manifolds, which are also interesting to lots of different people. And three-dimensional Calabi-Yaus are thought to, so string theorists, so this is where I like fly away from number theory and start talking about physics. But it's not really physics, it's more math than physics. So string theorists, so you know there's 3 dimensions in which we move in, and then we can think of a time dimension, right? So we sort of live in 4-dimensional world. But people think, or physicists, string theorists think, that there are 3 hidden dimensions, complex dimensions, so really like 6 dimensions, right? And they are said to be explained by a Calabi-Yau manifold. So these are my buzzwords. So to see that these are things that other people care about. And then there's this conjecture that some physicists made that in mathematics, the mathematical version of that conjecture is called mirror symmetry. Have you heard those words? So mirror symmetry, the conjecture essentially states that Calabi-Yau manifolds come in pairs. Okay? These Calabi-Yau manifolds come in pairs. And so these K3 surfaces also come in pairs. But these are surfaces, so they're 2-dimensional objects, right? These are 3-dimensional, the ones that from string theory. So what I do is study what is called arithmetic mirror symmetry, which means that I am taking, and so again, like when you put arithmetic in front of any math thing, it just means like you're counting something. Okay, so arithmetic geometry, we tend to count points a lot on some geometric object, right? Like a curve or a surface. In arithmetic mirror symmetry, what we're trying to do is study the zeta functions of mirror pairs. So someone mentioned zeta function. This is not the Riemann zeta function. This is a zeta function associated to a geometric object. I'm getting somewhere, I promise. And so the zeta function, to be able to compute this, you need to know the number of points on a variety over a finite field. Okay? So this is sort of the way that I'm getting into this, is I count points because we want to compute zeta functions, because we want to look at zeta functions of mirror pairs and see what the conjectures are about that. We actually don't know very much about that. And then this is interesting to string theorists who want to understand the universe. So, you know, that's cool, right? And then in sort of a different tangent, this kind of stuff, counting points, is really useful in cryptography. Sometimes you want like an elliptic curve with lots of points, or you want an elliptic curve with very few points, depending on what kind of elliptic curve cryptography you're doing. And so this is sort of elliptic curve cryptography is like one of the most secure ones that there are, and it's very good because it doesn't use as much memory as others or much computer space as other crypto systems. And so I'm not going into that, but I'm just saying, so I promised, this is my part of where I promised I was going to answer the question, who cares, in my abstract. I don't know if you saw that. So I'm just telling you, who cares? Of course, I care. I just like seeing patterns like this. I do have very basic interest sometimes in number theory, which is like, wow, this is a hypergeometric function. Is this other thing also a hypergeometric function? This is kind of the naive way of doing math, but I like it. And then, but there's a bunch of other people who care, and hopefully you do now. So yeah, that's it. Thank you. Yes?
So where did the idea come to introduce the hypergeometric functions here? Because they're not blatantly obvious. I mean, they're not shouting at you, are they?
They are if you have looked at these things for a long time. But okay, so let me tell you. So there's what people call the Legendre family of elliptic curves. This is a very classical example of elliptic curves where lambda is the parameter. So an elliptic curve is usually a equation in two variables, and it's quadratic in one variable and cubic in the other. Right? I mean, there's more to elliptic curves, but that's essentially it. And then this lambda, this parameter, if you count the number of points over this elliptic curve as a function of the parameter, you get a hypergeometric function. And so someone figured that out a long time ago. And it's just by doing the computation, you can see there's like, I mean, these are almost binomial coefficients. And so you can do some arithmetic and see that that's what's going on. But the more interesting thing is elliptic curves have these other things associated called the periods. So there are these special integrals that have to do with the geometry, so with the cohomology. But elliptic curves can also be thought of, if you look at them in like as solutions in the reals, they're going to look something like this, like a little curve, right? But a complex curve is really a two-dimensional thing, right? Like the complex line is really a plane, correct? And so in complex terms, this is really a torus. So you're taking the complex plane and then you are doing something like modding out by a pair of vectors or by a lattice. And these guys that generate the lattice, it tells you what, those are the periods. So there's something that has to do with the geometry. When you get the differential equation that these guys satisfy, is the hypergeometric differential equation. So there's like two ways. I know I'm saying a lot of big words, so if you're bored, just do the homework. But I think this is really what is really fascinating to me is that there's this geometric, purely geometric thing that is exactly the same hypergeometric function that you get when you're just counting points, which is a purely arithmetic thing. And so this is the stuff that's really fascinating. And so I tried to do this for a more general family that's more general than this, called the Dwork family of hypergeometric of hypersurfaces, I mean. And so yeah, it's a great name. He wrote under a pseudonym for a while, and his pseudonym, you would think it would be like Bob Jones or something. It was Mauricio Boyarsky. That was his pseudonym, and his real name was Bernard Dwork. So I don't understand how that happened. But he was a student of John Tate's. So, you know. Anyway, so I I don't know, I just think this sort of relationship is fascinating. I don't know if this answers your question, but this is where I started thinking about this and why hypergeometric functions were interesting. And my advisor here also had done a few examples with physicists who worked in string theory, and they saw the same hypergeometric functions pop up for different reasons. And so he said, well, you look at this. That's how PhD theses start, by the way. It's like, hey, I found something. Go work on it. You know. So, any other questions?
Is it proven to be a hypergeometric function, or
Yeah.
you just guess and check?
No. I proved this.
Okay.
Yes. And in general. So, and my paper is on the archive. So it's actually coming out next month, but it's not published yet. And my webpage. So, but yeah, I did this in general for this family with only 2 variables, and then less generally for a more general family. So you know, you can breadth or depth. Like you can't do both necessarily, but.
But in general, do we know that, like, if you have a homogeneous equation of how many variables, do we know that it's always given the number and lambda is always no?
No. This is what I'm really this is like sort of my life goal. So for some examples it is known, for some examples it's not clear. But every example I've tried to compute, this is what I end up getting. So my suspicion is that at least for nice manifolds like Calabi-Yao's, this is going to be true. But it's not known that this is generally the case. But this is again why it's fascinating, because it keeps showing up, but you don't know in general. Other questions? Yes?
Where does the mode 7 come from? Does that have any meaning or just randomly?
Oh, mod 7? I mean, I just did it for 7 because I wanted to have a specific prime so that I could show you like this, something specific. In general, it's going to look more like this, right? And so this is going to be mod. Actually, this is going to be mod Q. This part is always the same for this variety. But mod 7 is just because I wanted to do 7. Is that the question? Or is it like the modding out?
Yeah, so you just pick mod 7 because it have lots of implications, meaning that there is no more than 7 solutions for each lambda.
No, right. So I just did mod 7 because I wanted to do this computation and show you something specific that was a polynomial.
You could find a pattern changing the mod.
This works mod p for any p that 3 has to divide p minus 1. That's the only restriction on p. So there is a restriction on p, but it's just that 3 divides it.
So
Yes.
why do you mod out in general?
Yeah, so it's going to be a little bit more complicated. It's going to have other hypergeometric stuff if you do mod something bigger. But it doesn't. This is mainly because the problem that I was looking at, this problem was what they found was a number of points mod p. And so I really wanted to literally have the exact same example in a different variety, where the geometry, see, and the other problem is now there's no interesting geometry here. This is actually a 0-dimensional manifold, which means a bunch of points. So it's no longer like the differential equation. I just wanted to count the points and know that no matter what the degree and the prime, this would going to be this hypergeometric function modulo that prime. It is a little bit trickier when you do mod higher powers of p. But if you do mod a large enough p, you get all the information you need. So because you can mod out by bigger powers of p, and you're still going to get the same hypergeometric functions, the same number of points. Right, because if you have a finite number of points, you mod out by a p that's much bigger, it's not going to change that number of points, right? And so these are things that I've been trying to generalize in different ways, but this was the computation I did.
Just to be clear, the smaller form, mod 7, that would change if the prime was different or not?
Yes,
Yeah.
that would change if the prime is different. This would not change if the prime is different. This only depends on the equation. That depends on 7. Well, and P. I mean, it does depend on P in a sense, but just that P has this property. Yes?
Does the constant C have a secret value?
It's the number of points if the lambda is 0. I just didn't want to obfuscate what was going on. I mean, it's just, if this is x cubed plus y cubed equals 0, is the number of solutions to that. And there's like a well-known formula for that. The Vey actually proved that for anything that looks, this is called like a Fermat surface or Fermat hypersurface, when it's just x to the n plus y to the n plus whatever to the n. So that's well known. So this is why I didn't look at this. I just looked at this. Yeah.
Would it be n of 0 minus 1? Because you have n of 0 here. C would be n of 0 minus 1.
Make sure C is that.
What?
You're saying why don't you drop the 1 into the C?
Oh, I see. Yeah. This 1 comes from this chunk, not from counting the points as 0.
So I'm saying that C wouldn't be n of 0, but it would be n of 0 minus 1, wouldn't it?
Why?
Because, sorry.
Oh, because if you plug in 0 here, you mean? Wait. Well, I don't know. But I think it's right like this. But I can talk about it more. Or think about it more. But I think it's that.
Is there any more questions?
Is there a reason for the restriction?
3 divides p minus 1?
No, the 0 to 1 is the
Yes. I mean, it just so that I could write it as a hypergeometric series. Like I could write it like this. What I identified when I was writing these things out is that it's only these pieces of the hypergeometric series that show up in this description. So it's not the whole hypergeometric series. That's the only reason.
This is more of like a concern.
Mm-hmm.
So these hypergeometric functions, they go over a lot. Like a lot of functions are in this form, right?
Mm-hmm.
So how is it that it surprises you every time that you can write a number of solutions in this form? Maybe.
Well, many special functions can be hypergeometric functions, but not all interesting functions are hypergeometric, right? So, is that your concern?
I'm just saying
That they're not that interesting? No, but I mean, so yeah, there are a lot, but I don't understand your concern.
I'm just saying that there are a lot to not be surprised.
Well, maybe this is more of a philosophical, what are you surprised by and what am I surprised by? But I feel like this is a very specific pattern that I don't think is that obvious. I mean, I don't think you could predict things like what parameters are associated to this counting of points and where does that come from. And I mean, I just find it surprising because it could be that hypergeometric functions are just some interesting special functions that don't count things. But what my suspicion is that hypergeometric functions have to do with counting in general. And I don't think that's not obvious to me. Maybe, I don't know. I'm still surprised and excited. So, but you are free not to be. So it's okay. Yeah.
Why is it that 3 has to divide p minus 1? Why can't you just pick a non-characteristic 3?
That is just like some restriction I found when I was working this out. I mean, I remember where it comes from. It's not like that enlightening if I explain it. So it's just sometimes you have to do this. And then this example, the new one that I've been working with, I have like 4 special cases. What if 7 divides p minus 1? What if 7 does not divide p minus 1? And so like I have like a tree of cases because it changes a little bit from one case to the other. And in this case, it was just, I was using previous results that had this restriction, and that restriction came from some thing that happens when it doesn't divide it. I don't know, but yeah.
Let's thank our speaker.
Thank you. And thanks again for coming and inviting me.